Hi everyone, welcome back to Physics 11. So this is going to be the last video for the energy unit. So far we talked about energy, work, kinetic energy, potential energy, and then we talked about conservation of energy, which is basically combining potential and kinetic energy together. Now, in the past I mentioned that we might introduce heat into our equation for the conservation of energy once you start including friction in your calculations, because in real life, whenever you transform one type of energy into another, some of it will also get lost to friction. And we have to include it at some point in our calculations to be more accurate. So that's the unit that we're going to look at some of those cases where we want to include friction. So some of the energy that will be transformed into heat. So let's talk about thermal energy. So thermal energy, normally when you think about thermal energy, normally you think of something that's being burned. For example, here we have a combustion of some sort of material, perhaps gasoline or gas. And you think of a fireball, right? But thermal energy doesn't have to be something that's combusting. So let's take a look at some of the definitions. So here we have thermal energy versus temperature. And hopefully this might ring a bell a little bit from your junior sciences when you learned about kinetic molecular theory. So thermal energy, or letter Q, which is used a lot in chemistry, is the total kinetic and stored potential energy within an object. So this means that the energy that is within the object either has kinetic energy or has the potential to be transformed into kinetic energy. At the same time, some of it, whenever you again transform energy from one type to another, will be transformed into heat. And then we have temperature. So temperature is the average kinetic energy of the particles within the object. So again, temperature is the average kinetic energy of the particles within the object. Thermal energy is the total kinetic and stored potential energy within the object. So the more mass you have, basically the more thermal energy you will have. So let's take a look at one example. Here we have a question which contains more heat, a pot of boiling water, or an iceberg. So this is a classic question that you encounter in your thermodynamics class. So when they ask you for which contains more heat, they ask for thermal energy here. So we have a boiling pot of water on the left, and we have a giant iceberg on the right side. So the boiling pot of water, if it's at sea level, this would be at around 100 degrees Celsius. So water starts to evaporate 100 degrees at sea level. And the iceberg here is made of solid ice. Ice forms at 0 degrees, so this could be 0 or below 0. So let's say it's 0. So the question is then, let's first look at temperature. This, of course, is higher temperature. This is at 100 degrees. This is at 0 degrees, right? So let's make a note here. So 100 degrees Celsius, this is going to be at 0 degrees Celsius or below 0. But then the question is not asking us about temperature. The question is asking us which contains more heat, so which contains more thermal energy. Now, the amount of matter that we have in the pot is very small compared to the amount of matter that we have in this giant iceberg. Because the amount of matter is so little in the pot, even though this has more kinetic energy because the molecules are at higher temperature, the molecules in the iceberg, they still move. They might vibrate a little bit, not as much as in the pot of boiling water, of course, but because there's so many more of them, this will have greater thermal energy. So this is more thermal energy, and this one will have less thermal energy. Okay, just because of the amount of mass they have. You have maybe, I don't know, maybe there's 2 or 3 liters of water in the boiling pot of water, and this could be tons and tons of water in the iceberg. So even though the average amount of vibration that you have in the iceberg is very small, but because there's so many molecules, altogether they add to a lot more thermal energy compared to the boiling pot of water. So what else can we say about this? Let's review a little bit our states of matter. So if you have, if you remember, atoms and molecules are in constant motion, so this is again your kinetic molecular theory. If you have a solid, a true solid, which makes a crystal, they will form a pattern or a lattice, which means the atoms or molecules will arrange in specific patterns. So for example, if you think back to your ionic and covalent compounds, for example, like table salt, sodium chlorate, it's an ionic compound, it will make a cubic shape. And I can't think, let's say if this was water, it will make a tetrahedron shape. So kind of like a little pyramid, three-sided pyramid. That's a covalent bond. So they will organize and have a pattern. So that's a solid. So they can move as a group, they can vibrate as a group, but they cannot, each molecule or each atom cannot move separately in a solid. Whereas in a liquid, each atom or molecule, normally molecules, because if this was an ionic compound, it'd probably start forming some sort of solid, but each molecule or particle, I'd just say particle to be general, is just moving around, not making any patterns, okay? So they have a bit more kinetic energy. So this can have a little bit of kinetic energy. This will definitely have more kinetic energy because the particles may have a little bit of velocity, so we can add little velocity vectors like so. But again, they don't have enough velocity to be bouncing around the containers, so they have a little bit of velocity, but not a lot. And then, of course, in a gas state, the molecules have a lot of kinetic energy, which means that these guys are bouncing around the container in every which way, so they have a lot of velocity. See, we can add some velocity vectors to show that these are moving around. Okay, so this has the least amount of kinetic energy, liquid has some kinetic energy, and gas has the most kinetic energy. So also think of the space between them. Solids, normally they're the densest state. For example, water is not the case. Water is more dense in a liquid form compared to solid state. But generally speaking, you can also think of densities as solids are mostly more dense than liquids, and then of course gas is the least dense. So that's why they have a lot more space between them, and again, they're bouncing around all over the place. So when a material is heated, the molecules move faster as a result, and it will expand. So that's called thermal expansion. So for example, when you heat up a solid, the particles start to vibrate more and more, and therefore they will generate a bit more volume. So that's why it expands. In the liquid, of course, same thing happens, but now the molecules have more kinetic energy because that heat that you introduce will transform into kinetic energy. So these molecules start to move around more, and in the gas they move around even more, and then they bounce even more. So there is even more volume that they can occupy. So they will expand even more. So here's an example of a curve. So in this case, we have the heat curve for water. So if an object is heated, it will either increase temperature or change state. So let's say, depending where you start from, let's say if you start from liquid form, let's say you start with just water and you warm it up. Let's say start right at 50 degrees, right? If you heat it up, let's say to 100 degrees, again, if you're near sea level, the water will start to boil, but it doesn't boil right away. So we have this area here where the water is turning to steam, but it's not all steam. So we have this mix of water and steam forming, but again, it's not all steam. So this is called latent heat. So basically, whenever you have these transitions from, or change of state, you have these transition periods where you have to still keep introducing heat until it completely changes state. So same thing happens down here. Let's say if you were to put the water in the freezer and the temperature is gonna go down the other way, so you're gonna get down to 0 degrees, right? So now it starts to become ice, but it doesn't become ice right away. you start having some ice on the surface, and then eventually all the water changes from liquid to solid, and then of course you will have ice after that. So again, we have this transition period here from liquid to solid. So this is similar for other materials as well. You have these different transition periods between different states, and depending on the material, these can be more or less. So that's why we have a table of values with different heat capacities for each material. So again, this is for water, but you have similar curves for all sorts of different materials. So if you go into engineer, for example, there's like loads and loads of tables that you're gonna see and have to remember and use in your work, because there's especially if you take something like material science, you're going to be looking at a lot of this. Also, if you take thermodynamics, you're going to look at a lot of the steam curves and stuff like that. Now, how can we transfer heat? Well, there are three ways. There's conduction, convection, and radiation. And also remember that heat always goes from high to low concentration. So let's think about conduction. Now, there's a whole unit in, I believe, chapter 14 in our textbook that talks about heat, temperature, and transfer of heat. So conduction is basically direct contact. Let's say if you have a hot object, like in this case we have fire here, and you stick, let's say, an iron rod or iron pick into the fire is in direct contact, or the log is in direct contact with this iron. So it doesn't have to be fire, right? You can have, for example, hot coffee in a mug, and the coffee is in direct contact with the mug itself, so it's transferring heat to the mug, so the mug starts to get hot, right? So that's conduction, that's direct contact. So you can make a note here, direct contact. Okay? Then we have convection. Now, for convection to happen, we need to have some sort of medium. We need to have an atmosphere. We need to have a gas. So for convection, basically what happens is if you have a hot object, let's say like this campfire here, the air molecules around the fire will receive some of that heat, which will then transform into kinetic energy, which means the molecules near the fire now can fly further. They have higher velocity vectors, and they can bounce into more molecules near them. So that means they're going to transfer this heat to other molecules next to them. And of course, the further you go, the more times they're going to bounce into other molecules. So eventually they will lose some of that kinetic energy, and they will slow down, so the temperature will drop again. But again, convection is basically due to motion of particles. So due to motion of particles between two objects. For example, we have a fire here, we have a campfire, and we have our hands. So we're not touching the fire directly, we're just getting close to it. And again, because of the particles, air molecules in this case, are bouncing around and they're transferring the heat to us. And the last one is called radiation. Now, radiation is electromagnetic waves. So this is going to be E and M, so electro magnetic waves. Now, everything emits some sort of radiation. When we talk about heat, we're talking about infrared radiation. So that's the type of electromagnetic wave frequency that we can't see, but we can feel it. Some animals can see infrared, but we can't. For example, our eyes can't see it. It's just right below the visible spectrum. So you can see from red to violet. So infrared is below red, but we can feel it. And then, of course, after that, we have ultraviolet, for example, which is harmful to us. And then we have X-rays, which also harmful to us. And we have gamma rays and so on. So higher frequency, which basically carries enough energy to ionize your particles, which can then destroy your DNA or your molecules, which can cause cancer, for example. So UV rays are basically higher frequency energy waves. So anyway, radiation is something that depends on the type of energy, depends on the type of elements that are being heated. So we all release some sort of energy. Our bodies release some electromagnetic waves as well. For example, in space, because there is no atmosphere, there is no convection. And because they can't just have a heat sink some sort, like you can't just put your spaceship next to something that will absorb the heat from the spaceship, there's no conduction. So in space, the only way to dissipate heat is through radiation, which is actually a big challenge, big engineering challenge for them, because that's the only way they can dissipate heat. So for example, if you have machines running and they're creating heat, you have to cool them down somehow. So the only way they can do this is through radiation. So lucky for us on Earth, we have an atmosphere, so we can have convection, and of course, we have enough mass on the planet that we can also use conduction. So again, all this happens until equilibrium is reached. So at some point, if you have a closed system, let's say if you have a room and you have a cup of coffee, at some point the cup of coffee will reach the same temperature as the room, right? So that would be the equilibrium point. Now let's take a look at the equation for heat transfer. Now the amount of heat transfer is found with the following equation. So Q stands for the change in energy or heat or thermal energy. And then this equals to mc delta T. So our Q is the change in thermal energy, and this measured in joules. So this is basically unit energy. So again, thermal energy. Now, depending on the type of question you might be working on, if you're just talking about heat capacities and thermal energy, you're probably going to be using the Q notation. But if you start to combine it with kinetic and potential energies, you might want to use this notation, because remember, we've used E with the subscript for kinetic and subscript for potential energy, so we can use the same thing, same type of notation for thermal energy. But anyway, in my notes, you might see a mix of both of these, especially in the answer keys, either Q or delta EH. So just so you know, that stands for thermal energy. Now, of course, M is the mass, now measured in kilograms. So you have to remember, whenever you have something that's in grams or milligrams or tons or whatever the other units might be, or pounds, make sure you always convert to kilograms. That's the unit that we use in a SI system. Now, the C here is called the specific heat capacity, and this is measured in joules per kilogram Celsius. And this will depend on the type of material that you're working with. And delta T, of course, is change in temperature, which means your final minus initial temperature. So let's take a look at an example where we have some element that's being heated up. So before we get to that, I guess here's a quick table with some of the specific heat capacities for different materials. So we have water, we have carbon, iron, copper, and lead. So if you look at the water, water can actually absorb quite a bit of energy before it changes states, right? So water has really high specific heat capacity. So it acts as a good buffer, right? And avoid changes in states. For example, that's the reason why cities near the ocean, for example, like Vancouver, has milder climate, because the water near us acts as a buffer because it has a high specific heat capacity. So it can absorb a lot of heat, and it can also then return this heat to us, to the atmosphere. So basically that's why it works in both ways. Whereas, for example, carbon and other materials here, as you can see, metals, they have very low specific heat capacity. So basically, if you start to heat it up, it will change a lot faster its state. So let's take a look at the example. So here's an example. It says, let's say you make a cup of coffee and you're boiling by boiling 250 grams of water that is initially at 15 degrees Celsius. How much heat is needed? So in order to find the answer to this, let's write an equation. Q equals to mc delta T. So remember, we use capital T for temperature, lowercase t for time, so do not confuse those, do not make the mistake of writing lowercase t. So our Q is what we're trying to find. Now our mass is given to us, but it's in grams, so we had to change this to kilograms. So 250 grams is going to be quarter of a kilogram, or 0.250 kilograms. Now the C here is going to be the specific heat capacity for water, because we're dealing with water here. So it's going to be this value right here, 4180. Now again, the units are going to be joules per kilogram. Celsius. Now, you have to be careful with the tables for specific heat capacity. So these are going to be in joules per kilogram Celsius. Some tables may have this per gram. Okay, so be careful. Make sure you pay attention to the unit. So in this case, this is joules per kilogram Celsius. So we have our C value. Then we need our delta T. Now we know our initial TI is 15 degrees, so we're starting at 15 degrees. And then T final is going to be boiling water. So if we're near sea level, this is going to be 100 degrees. So that's something you have to know. Boiling temperature is 100 degrees near the sea level. So now that we have all the information, we can then plug it into our equation. So again, our mass is going to be in kilograms. So we're going to enter 0.250. So 3 sig figs there. And then we have our, what do we have here? C, which is going to be 4180. Now this is a constant, so that's not going to count towards sig figs. And then our temperature, which is going to go from final, which is going to be 100 degrees. Now I had to include actually all the zeros here. So this is 100 with a decimal at the end, minus 15. So we're going to end up with the following. We're going to end up with 0.250. So again, 3 sig figs there, 4180. And here we're going to have, what is this, 85? Okay, so in the end, we should have 2 sig figs in our final answer after you do the subtraction there. So 0.25 times 4180 times 85, we get 88825 joules. So that's going to be the amount of energy that's needed to heat up the water from 15 degrees to 100 degrees. Now, of course, we need to round this to 2 decimals, or to 2 sig figs, I should say. So we can write this in, let's say, 8.9 times 10 to the 4th in scientific notation. So that's going to be the answer for this example. All right, so let's take a look at another example where we can then introduce friction basically into an energy problem. So we have a 35 kilogram child that goes down a 3.2 meters high slide. The child is initially at rest, and then it's going to move at 1.8 meters per second at the bottom of the slide. If the slide is made from 12 kilograms of iron, and all the heat is transferred into the slide, so basically from the friction, by how much does the temperature of the slide increase? So here's what we have. Here's our scenario. We have our slide. It goes down here, so we have our slide here, right? So here's our child at the top. So this is going to be our initial height, which is 3.2 meters. So it's a fairly high slide. And then, of course, at the bottom, it's going to be on the ground. So the height is going to be 0, but we're going to have a velocity, which is going to be 1.8. So this is going to be 1.8 meters per second. So that's going to be our scenario here. And of course, all the heat is going to be transferred to the slide, which is made of iron. So normally we just have the following equation. We have our initial potential. So E potential initial plus the EK initial equal the EP final plus EK final, right? So that's what we normally start with if we are not including friction or heat. But in this case, we are going to talk about friction. We're going to include the heat because we know that that's what actually happens. We do lose some of the energy, or we don't really lose it, but it gets transformed into heat. So we're going to include the Q here into our calculation. So this is going to be our total initial energy. Okay, and of course this is going to be our total final energy. So again, we don't lose any energy, it just gets transformed from one type into another. So again, because here we're going to include friction, So we're going to have some heat generated. We're going to introduce this Q here. So the question is, by how much does the temperature of the slide increase? Now the temperature change is going to be in our Q. So basically what we need to find is our Q here. Now before we go and start solving for Q, let's think about what's going on here. At the top of the slide, the child starts from rest, which means that there's no initial kinetic energy, which means we can make it equal to 0. Now at the bottom of the slide, he's going to be on the ground, so there's going to be no potential energy. So we can remove the gravitational potential energy. So all we have is then the EPI equal to EKF plus Q. So that's our equation that we now have. So let me write it on the left here. So EPI equal to EKF plus Q. So our goal is to find Q here, from which we can then find the change in temperature, delta T. All right, so potential energy is just going to be, actually, let's just solve this for Q and then replace the values. So Q is going to equal to basically move the kinetic to the left, so we get EPI minus EKF. So now we have the Q by itself. Now we can plug in the values or expand this further. We have mgh. Now this is the mass of the child here. So because we have two different masses, we're dealing with the mass of the slide itself. So let me introduce mass of the child minus, and this is our initial height here. And kinetic energy is 1/2 m. Again, this is the child, so mc times v final squared. Okay, that's what Q equals to. So let's expand this further. And because we're looking for the temperature, let's write the equation for Q. So remember, Q equals to mc delta T, right? So we're looking for the delta T. So we're going to replace our Q with the M. Now this M here corresponds to the iron slide. So this is going to be, let's write the symbol for iron, Fe, so we don't get confused with initial. So the mass of the iron slide times the specific heat capacity for iron, which we need to go back and look up in their table there, times the change in temperature, which is what we're trying to find. We're trying to find delta T equals to the following. Now in this, we have MC in both of them, so we can actually factor the MC out if you want. So we can do this. We can do the MC factored out, so you're going to be left with G times HI minus 1/2 V final squared. Okay, and then of course to get delta T, we need to divide both sides by the M iron and the specific heat for iron. So delta T in the end is going to equal all this stuff on the right divided by MFE times C. So we're going to get MC times GHI minus 1/2 VF squared over the mass of the iron slide times the specific heat capacity of iron. All right, so that's our equation that we're trying to find here, which is going to allow us to get our change in temperature. So the next goal is, of course, plug in all the values for all of this stuff. So let's plug in the mass. So the child is 35 kilograms. Then we have our 9.8 for gravity. I guess I need a second set of parentheses here. So let me use a square bracket here. So this is going to be 9.8 times the height, which is 3.2. Then we have minus 1/2. And the velocity is 1.8 squared. 1.8 squared, close the bracket. And all of this then over the mass of the iron, which is 12 kilograms, times the specific heat for iron. So let's go back and look at that. So iron is 460 joules per kilogram Celsius. So 460 is what we need to include here. 460. All right. And that's our calculation. So on the calculator, you have to do the square brackets first. So you have to do the multiplication 9.8 times 3.2 minus 1/2 times 1.8. So here we're going to end up with, we should end up with well, let's see, 9.8 times 3.2, that's 31.36. We should get two sig figs, or one decimal rather. I think in the end. Minus 0.5 times 1.8. So that's 30.46. So we should be getting two sig figs from this calculation times 35, which is two sig figs. So that's 1066.1. And then on the bottom we have two sig figs. So the final answer should have two sig figs. So all of that, which is 1066.1. Again, I'm just showing the middle step. You can just keep doing this on the calculator. And then you're going to divide this by 12 times 460, which is going to be 5,520. And 1066.1 divided by that is going to give us 0.19 degrees Celsius. So as you can see here, our delta T, our change in temperature, was less than a degree, of course. That's like 1/5 of a degree. So it's very minor. So, but that's why we normally don't include heat when we start learning about energy, because as you can see here, the amount of energy that actually gets transformed from friction into thermal energy is very small. So that's why a lot of times we actually exclude this or don't bother with the heat calculation because it's not a lot of energy. Now, of course, depending, well, in this case, we're talking about temperature, not energy. Of course, depending on the type of calculations trying to do, sometimes you have to include all these steps because, let's say if this was some sort of experiment, scientific experiment, you want to control your temperature precisely, then you have to include all of the energies. You can't just exclude friction. That would be really important to include that. All right, so if you have any more questions, make sure you post them as a reply in Teams, and make sure you read the chapter 14 in the textbook, which covers thermal energy and covers heat transfer. And I think section 13.1 also talks about temperature. So in case you forgot what temperature is, or if you want to have more information on that, make sure you read the textbook, section 13.1 in chapter 14. All right, so that's all for now. Make sure you do the practice questions, which involve heat transfer and friction.